Now we're looking at exponential functions. Exponential functions are functions that a lot of times map the growth of certain things in real life applications, like the growth of a bacteria, or maybe even the decay rate of things. Exponential functions, these are in the form of y equals a raised to the x power, where a is equal to a real number. Our value of a, this has to be greater than 0 in order for it to be an exponential function, and a can't be 1. If a was negative and then you were raising it to different powers, it would be bouncing back and forth between positive and negative numbers. If a was equal to 1, well, 1 raised to any power is 1, and so we would just have a horizontal line through y equals 1. So those are why those values need to hold true. So depending on if a is a value which is bigger than 1, or if a is a number between 0 and 1, depends on what the graph is going to look like. And so let's just look at a simple graph really quickly, and let's graph y equals 2 to the x. So if we were going to do this, we could just plot some points. So if x is 0, recall any number raised to the 0 power other than 0 is 1. So 2 raised to the 0 power is 1. So we have a point here at 0, 1. If you plug in 1 for x, you get 2 to the first power, which is 2. If we plug in 2 for x, we get 2 squared, which is 4. If we plug in -1 for x, so recall negative exponents, we can make those positive by bringing them down into the denominator. So if it's a negative exponent in the numerator, bring that piece down to the denominator to make it positive. So if I'm looking at 2 raised to the -1 power, this is going to be 1 over 2 to the first power, or 1/2. So at x equals -1, I have 1/2. At x equals -2, I'll make our exponent positive, bring it down to the denominator, I get 1 over 2 squared, or 1/4. So at -2, I get 1/4. If we look at this, this is our graph. So this is actually the general shape of y equals b to the x, where your base is bigger than 1. So notice that we have some properties going on. So the properties of this graph, y equals 2 to the x. Well, notice we have a horizontal asymptote on our x-axis. As x is going to -infinity, and remember we looked at how to write that. So the limit LIM as x goes to -infinity of b raised to the x power. This is going to the y value of 0. So another way to say that is we have a horizontal asymptote at 0. At y equals 0. So look at our domain. So our domain of this f of x, b to the x, notice that there's no trouble spots. We can plug any value in for x and it will spit out a number. So our domain is going to be all real numbers, -infinity to infinity. Our range Well, we have a horizontal asymptote at 0. There's no value of x that would give us back 0 for y, and there's no value of x which would give us a negative number for y. And so our range is everything from 0, not including, so a parentheses 0 to infinity. And then a point that's always going to be on this graph unless we have some transformations going on, but is going to be the point 0, 1. So 0, 1 point on the graph. Okay, so now let's look at the case where your base is between 0 and 1 and what the graph would look like there. So let's graph y equals 1/2 raised to the x power. And so if we do this, if we start plotting points when x is 0, well, 1/2 raised to the 0 power is just 1. If we raise 1/2 to the first power, we get back 1/2. If we square 1/2, 1/2 times 1/2 is 1/4. If we raise 1/2 to the -1 power, we can make, if we have a fraction and that's raised to a negative exponent, we could flip what our fraction, take the reciprocal and make that exponent positive. So this is the same thing as 2 over 1 to the first power, or 2. So x is -1, we get back y is 2. X is -2. We can flip what's inside, change our exponent outside to be positive, and then squaring 2 gives us 4. And so we get a graph that looks like this. And this is our general shape. Of y equals b raised to the x power, where b is between 0 and 1. And so we have similar properties. Notice we have, again, a horizontal asymptote at y equals 0. If we look at the limit as x is going, in this case, off to infinity, this goes to 0. We have our domain is still our real numbers. Our range are all numbers bigger than 0. We still have a point 0, 1. In this case, and I forgot to mention it up here, and we look at about increasing or decreasing, when our base is between 0 and 1, this is strictly decreasing. And when we look at the graph where it's b is bigger than 1, this is going to be strictly increasing. Okay. So you should be able to now look at graphs of exponentials and be able to apply our rules of transformations of graphs. So if I wanted a graph y equals 3 to the x minus 1, I know what the general graph of y equals 3 to the x looks like. It's going to look like this. And looking at this, that -1 or this -1, I know that that just shifts my graph down 1 unit. So what used to be my horizontal asymptote on my x-axis is now shifted down 1 unit. So now my horizontal asymptote is going to be the line y equals -1. I can think about this point here that was at 0, 1. Now if I shift it down 1 unit, that's now going to become at 0, 0. So I'm going to have some graph. Looks like this. Let's say, so if I asked me for my range, my y value is now -1, but not including to infinity. What if it said, let's graph y equals 3 raised to the 1 minus x power? Maybe let's rewrite this a little bit and then talk about the transformations that are happening. So we can rewrite this as y is equal to 3 raised to the -x plus 1. So the -x, that's changing the value of my sign of x. Changing that x sign is a reflection across the x-axis. And then this +1 here, think of it as inside the parentheses. So this +1, this shifts it to the left. So if we kind of think about the transformations that are being done, well, if I first reflect this across the x-axis, that's going to give me something that looks like this. And then if I take this and I shift it to the left one, this point that is here at 0, 1 is now going to become at 1, 1. And so we look something like this. So that hasn't changed. Reflecting across the x-axis or shifting it to the left one has not changed what my where my asymptote is or what my range is. Let's look at one more. Let's say we want to graph y equals 1 minus 3 raised to the x power. That helps you. We can rewrite it. Another way to say this is y is -3 raised to the x. Think of this negative as out front here. That's not, our base is not -3. Our base is 3, and then it's multiplied by this -1 out here. And then we have this +1. So the minus in front of the 3x, that's a reflection, right? It's changing the sign of my y value. So this is actually a reflection across my x-axis. And then that +1, this shifts us up 1 unit. So if we think about our transformations going on, reflection across the x-axis is now going to look like, okay, sorry, I got to think about this. It's going to look like this. So this is y equals -3 raised to the x. And so now shift it up 1, that point that was at 0, -1 is now at 0, 0. And so our asymptote, that was our horizontal asymptote, is now going to be the line y equals 1. So you should be able to do general sketches of our graphs based off of transformations of graphs. So this is not all of 6.3, but it's a big majority of 6.3. So we'll finish off exponential functions on Thursday, and we'll jump into logarithms and rules and properties of logarithms and how to solve logarithms, how to graph logarithms, etc.